So this is the last topic. Oh, actually, can someone start recording, guys, please? Okay. Oh, thanks. So far we've seen, or we consider, one electron in a field of atoms, right, of a solid. And as I said, the thing is that we actually have more than one electron, and there's actually 10 to the 22 valence electrons that can be found. And it's impossible to know the place and the energy of all these electrons, but we can sort of try to get a function that tells me the probability of where the electrons are, and basically the distribution of those electrons, and that's what we're going to focus on. And that's related to the Fermi energy, right? So I already said this. I already mentioned this slide and mentioned you can see there a table with some of the Fermi energy values for some metals. Okay. So if we think, and how are we going to try to describe this whole bunch of electrons that are present in a solid? Well, there is one distribution that actually allows me to do that, and that's known as the Fermi Dirac distribution, or the Fermi Dirac statistics. I'm not sure if you've ever seen that in statistics, but that's basically what we're going to use. So this distribution or this formula basically allows me to determine the distribution of the energies of a large number of particles, and obviously within that concept of particles we have the electrons, and also how those electrons or how those particles change with temperature, right? And how the energy changes with temperature. So that's what we're going to use. And so basically this equation that you're looking at right now, that is known as the Fermi function. Sorry, and that equation tells me the probability that a certain energy level is occupied. So if you remember, this is a probability. Therefore, this equation is only going to go, or ideally, or we're going to sort of try to put it in a place where we can get a value from 0 to 1, right? Because at the end, this equation, this statistics, this Fermi function is just representing what the probability of a certain energy level to be occupied is. And you see here maybe a couple of new terms. You see this EF term here. Well, that's the Fermi energy. Okay, that's the Fermi energy. And this KB, I'm sure you've seen it before. What's this KB term, guys? And I think I think somebody already said that last class. Guys?
Boltzmann constant.
It's the Boltzmann constant, right? So this is the energy, right? So basically it's the difference, well, obviously this is exponential, the difference between energy and the Fermi energy by the Boltzmann constant times temperature. So if this equals 1, what's going to happen, guys, if that's equal to 1? It means an energy level is completely occupied by electrons, right? Because these equations, as I said, it's basically telling me the probability that a certain energy level is occupied. So if it's 1, well, it means the energy level E, in this case called E, right, is completely occupied. Whereas if I get 0, that means that that energy level is empty. So it's unoccupied by electrons. Okay? So think of this equation. How do you think it's gonna look like? Well, the Fermi function, if we plot the energy versus the probability, so versus the Fermi function, we will get something like this, right? This is one chance, or this is one option. Do you think this makes sense, guys? For t equals 0, what happens when t equals 0?
The Fermi function would be 1 divided by 2.
The Fermi function will be.
No,
Sorry?
I'm confused. No. Forget that.
Okay, no, it's okay. So what happens if t equals 0?
There's no electrons in that.
T equals 0, not the Fermi energy. T equals 0. T, temperature.
Wouldn't that be the absolute zero?
Yes. So just looking at the equation, if t equals 0, what happens with that equation? Or as t is approaching 0, what's happening with the equation?
So numbers over 0, and this is infinite.
Yes.
In the argument of the function, and this the
So
function is undefined.
well, yeah, but I mean, in general, as t approaches 0, what's going to happen with this term? That's going to be infinity, right? In 1 over infinity, it's basically 0. I mean, I know we're not mathematicians. I know if you're going to say, oh, but if that's infinity, then it's undefined. Yes, I know, but the idea is if t is approaching 0, it's not 0, but if it's approaching 0, this term is going to be huge, right? This term is going to be so big, and 1 divided by that term is going to be 0, basically. That true or no?
Yes, that's true.
I'm agree.
Not sure. Think about it, guys. It's math. This is just math. Think about it. Maybe do it in your own notebook. Okay. Let's just analyze the graph first. I guess that's going to be more understandable now. If you look at the graph, when t equals 0, something happens, right? With the graph. We have certain, we have a probability, okay, that from 1 suddenly jumps to 0, right? It's in 1, so everything is 1, 1, 1, 1, 1, 1, 1. And suddenly, this is not a smooth change, right? This is a quick change, a rapid change, and this jumps to 0, right? Right at this level. That level is actually called the Fermi energy, right? So you can see from that figure that when t equals 0 or approaching 0, all energy levels that have an energy smaller, all energy levels that have an energy smaller, what is that, than the EF, what does that mean? So all energies that are in this range, all energy levels that are in this range, what happens with all those levels? Well, are completely filled because they have a probability of 1. Whereas those levels that are above the Fermi energy, when t equals 0, so that means the energy levels that are here, what happens with all those levels? Well, those levels have a probability of 0, so that means they're unoccupied. So what you can say from the Fermi energy now, if just with this graph you were asked to mention a concept of what the Fermi energy is, what will you say about this Fermi energy?
Hello.
Yes.
Okay, I think that with that graph, we can say that the energy, the Fermi energy, is the minimum or the base level of energy that every electron will have at temperatures near zero, or I don't know how is the graph when the temperature is different.
Okay. So now, I'm going to show you that.
So I can say that at in the concept that I was saying that it's the base level of energy of an electron in any temperature. So that's why I want to.
Yeah. Okay. I'll show you right now. But let's remember this. We define the Fermi energy. This is the usual concept, right? Is the highest energy that the electrons assume when t equals 0. That's the concept you will find almost everywhere. The Fermi energy is defined as the highest energy that the electrons can assume when t equals 0. And I mean, that makes sense now that I see the graph, right? Because this is the highest energy, because that means electrons are occupying an energy level. If electrons go actually above, or if I go above this energy, this Fermi energy, I realize that I actually have energy levels that are unoccupied. So that means I have no electrons there. Therefore, the electrons, as that says, it's basically the highest energy that electrons can assume when t equals 0. Now, what happens, as Miguel said, what happens when t is not equal to 0? Well, I mean, you guys can plot this function. You guys can just go and plot it in your computer, and you'll see it actually looks like this. What happens when t is not equal to 0? So you see there's actually a gradual change, right? You see there is a gradual change. And now what happens, now look at the graph. What happens with the Fermi energy? How do you define, just looking at the graph, how do you define the Fermi energy now? You could say, right? You could say that is actually the highest energy that electrons can assume, right? To have a 50% probability, because if you see actually how it's defined, the Fermi energy when t is not equal to 0, is actually the level when the probability, that means when the Fermi function is equals a half, right? So basically, when you have a chance of a 50% occupied energy level, right? And in general, you will say, I mean, and actually you will say that up to that point, and the concept remains the same, right? Even though, yes, you could say that you have let's say a quarter probability somewhere around here, right? And you still could easily argue that, well, you have a quarter probability being around here, a quarter of a probability of have an occupied energy level. But in general, this is the general concept for Fermi energy, right? Is that actually is the highest energy that electrons can assume. Yeah. Even if t is not equal to 0, yeah, because you see the graph, t is not equal to 0, and yes, you can have above the Fermi energy, you see still some allowed values of energy, right? Before actually the probability becomes completely 0, right? You still see above the Fermi energy some energy values or some energy levels that are allowed. You do see them, yes. But, just to simplify things and make this concept easier, that's how they define it, as the highest energy that electrons can assume. Now, you can see here that the thing is, when t is not equal to 0, which is, real case, this is not a sudden change. This is actually a gradual change. It goes sort of step by step, right? And in general, you can see this is actually quite important. This delta E value that here in the graph is just exaggerated. Actually, this value is usually sort of 0.5% of the Fermi energy, usually, right? Is usually around 0.5% of the Fermi energy, or let's say 0.5 to 1% of the Fermi energy. Obviously, just to make the graph more visible, here it's exaggerated, but there is a gradual change, and that's the point, right? It's not as sudden as in this case when t equals 0, right? But this is basically how this function, if you plot E versus f of E, you will get this. You will get these functions, okay? And this is so important. Because again, this is basically telling me, or this is going to be useful for real case scenarios, because as I said, the solids have so many electrons. They don't have only one valence electron. They have millions, billions of electrons. And even though we're not able to know where those electrons are and what the energies of those electrons are, we can use this equation and we can use these graphs, the Fermi function, to sort of understand the behavior of the whole bunch of electrons as a group. That means just the probability of those electrons in a group. Okay, now what happens or when do you think I will have this case? The Fermi energy becomes this. From this becomes this. Oops, becomes that.
David, just a quick question. Yeah, can we go back to the previous graph? Yeah, can I read the right graph? Let's say there's a 50% probability that the electrons have the highest level of energy. Can I read it like that?
I mean, you will say there's actually a 50% probability at that energy, at this energy, at the Fermi energy. You can say there's a 50% chance of an energy level that has this energy. You have 50% chance that that energy level is occupied. That's how you read it. So this is the probability of an energy level being occupied. So that means of electrons being there. If you want to say that, I mean, you could say, yeah, there is basically, I mean, you could say probably that you have half of the electrons that you will usually have in a full energy level, right? But that's actually, I mean, that would, you could relate that, but the actual thing or the actual meaning of this is that you have 50% chance at that energy, you have a 50% chance that the energy level will be occupied.
So in the left graph will be full chances for that energy level to be occupied.
Yes, so that's basically the Fermi energy. When t equals 0, below the Fermi energy, it will be 100% probability. So that means those energy levels will be occupied. Definitely, they will be occupied. Whereas if I have an energy above the Fermi energy, or an energy level that has the energy that's above the Fermi energy, then that energy level is definitely empty. So I have no electrons there.
Sounds good.
Okay. So when do I have this case, guys? E, just look at this, right? What's happening? I'm just eliminating this term, right? To eliminate that term, well, I need E much greater than EF. Because when E is much greater than EF, much greater. So that means the energy that I'm located at, it's just way above the Fermi energy. So let's say in the graph, I'm somewhere here, so way above the Fermi energy, right? This plus one term is meaningless because this is an exponential term, right? So this term is going to be huge. Plus one is like, okay, I have the huge term, right? So plus one is basically nonsense. So I can get rid of that plus one, and basically my Fermi function becomes this, right? Well, this is called the classical Boltzmann distribution. So as now you have two distributions or two functions. The Fermi Dirac one, that is the full one, right? And if I have energies way above the Fermi energy, then Boltzmann said, guys, actually we can use just this part of the equation, right? And so this is known as the classical Boltzmann distribution function, and this actually came from classical mechanics. It's this, you use this for thermodynamics. Well, you now use it for quantum mechanics, but this is basically from classical mechanics, and it's just because, again, we're assuming this, right? And there will be cases definitely that if we have energies way above the Fermi energy, right?
David.
Yes.
I have a question. By how much energy it is considered much higher?
I mean, if this term, it all depends on how big this term becomes. I mean, if you have a term, that's just maybe math. I mean, there's no really a value that you can say, oh, if it's, I don't know, 1 order of magnitude greater, then it's considered. That's just how big this term becomes. If you see that this term becomes so big that adding 1 to that term is meaningless, then you know you can use the Boltzmann function, right? It's just a matter of, I guess, saying, well, this is actually a huge difference. This term is going to be so big that it makes no sense to add a 1 to this value because anyways, it's still huge, right?
Okay.
I have a question.
Yes.
Can you present the graph of this distribution, but using the not this one. It could be the inverse. The inverse. I mean.
What do you mean the inverse?
I mean, we are seeing the energy as a function of the distribution.
Yes, of the probability. Yes.
So, I mean, I want to understand how did we all came up with the probability when the temperature is different than 0. The probability is the half of the energy. So I would like to know or to see if the function, if by graphing f versus e, we can see more clearly how this distribution, the probability came up.
I mean, you could plot it.
The thing is that I look for the function on internet, and I can't see how the probability changes. I mean, when I use a normal distribution, we can see more clearly that the probability becomes wider or narrower. But in this model, I can't see that. So.
Okay, wait. I don't quite understand what you mean. You're asking why is this changing?
No, why is that the probability become the half of the energy of the distribution?
Wait. No. It's not. I mean, you define it, and this is how, well, this is how they define. This is not something I did. They said, well, okay, for t equals 0, the Fermi energy is the highest energy that electrons can assume. So that means below the Fermi energy, when t equals 0, below it, all energy levels will be occupied because we know the probability is 1.
Yes.
And above that, we know the probability is 0. Now, if you use different values of t, so for t is not equal to 0, just forget about this value, okay? Just forget about the Fermi energy now. Just plot the graph. Just plot the graph E versus F of E, and well, it's obviously gonna change, right? And sorry, as I increase my energy level, obviously I'm gonna get my probability is gonna get towards 0, whereas if I decrease my energy level, my probability is gonna get towards 1. And so what they did is, okay, let's actually see where probability becomes half of it, and let's use that to define the Fermi energy. So that's how they define the Fermi energy. So they say, okay, actually, let's define it to the energy level where the probability becomes a half. It's just something arbitrary that they said, let's actually, because obviously this function is going to change. I mean, if you plot this function anywhere, and you can plot with the inverse axis, so you can plot f of e versus e, and this is going to be the same. I mean, you will get this picture, that plot, definitely. And all they said is, okay, guys, now where are we going to define the Fermi energy? They said, okay, actually, let's do something smart. Let's define it at the point where the probability becomes a half. So at that point, you go up to the energy and say, okay, so that point in energy is called the Fermi energy. Is that clear or not really?
Yes, now it's clear.
Okay. Okay, great.
Thank you.
Okay. Okay, so again, that's the case. So this is the Boltzmann function, right? Okay, great. Now, what do you think it happens when E is equal to EF and T is not equal to a half? Sorry, it's not equal to 0. So E equals EF, T is not equal to 0. What's happening when that occurs, guys? What happens with the function?
We have a half of probability.
Yes, and so what Miguel was asking, we have a half probability, and so they said, okay, that is the Fermi energy. Wait, actually, this should be capitalized because otherwise it looks like iron. Okay. So when E equals EF and T is not equal to 0, this probability is a half. And that's what they said, oh, okay, that's the Fermi energy. So if you want to say this, if you want to give an accurate definition of the Fermi energy, you can say it's the value of energy when the Fermi function is equals 1/2. That would be the Fermi energy. The Fermi energy is the value of energy when the Fermi function equals 1/2. And that is the definition, and that is actually, I guess, a more accurate definition of the Fermi energy, because it's real, right? It's almost it's impossible to get to the absolute 0 temperature. So the actual Fermi energy is the value of energy when the Fermi function becomes a half. Now, still related to Fermi function and Fermi energy, the density of states. How are energy levels distributed over a band? Because we have a band, right? A full band. Let's say, if you remember, actually, I guess I'll have to go back a lot, but just to see, you guys can see it clearly. This is a band, right? This is a whole band, this is another band. But how are the energy levels distributed along that band? Because remember, guys, that a band is not an energy level, okay? A band is not an energy level. We have energy levels within a band, okay? So it's obviously important to know how those energy levels are distributed within that band. How are the energy levels distributed over that band, among that band? And let's actually focus, and now we're gonna start using this term of valence band. We'll see later in more detail what the valence band is and what the conduction band is, okay? But for now, we're gonna use now this term of valence band. Why are we using the valence band? Because the electrons there are free. Because in valence band, remember, those are valence electrons. And valence electrons are electrons that are way or are far away from the nucleus. And so when they're far away from the nucleus, they can be considered free. Okay? And so we can use the case of the free electron, right? So it's basically, we assume the case of the electron gas or the free electron. Remember the first case we did. But now obviously those electrons are confined or are within a potential well, right? So remember, we did this case already, right? We already did this case of the potential well. So now we're talking about crystals, right? And we're talking about solids. So let's bring that back, that equation that we got for electrons in a potential well. Let's bring that back and if you remember, it's actually like that. And well, we define this as just saying a square, right? But it's that equation. If you go back to that case of the free electron in a potential well, we came up with this equation for the energy, right? Solving the Schrödinger equation, we came up with this equation. Now you're gonna ask me, wait, we didn't have A, maybe, because I don't think we had this value before, right? What do you think A is, guys? I think we gave it another name before. I don't remember if we used another letter for A before. But
It's the land.
Well, it's basically the lattice constant, right? So that means the length of the crystal, right? So this becomes the quantum numbers, and we'll see what they are later. And then we have pi, we all know that, the reduced Planck's constant, we have the mass, we all know that. And A now basically becomes the length of the crystal. So that means if you think of the potential well, so it's basically this, right? We have the well, so this is potential energy, right? Well, I guess potential energy. And this is length, right? So this is x, and that's potential energy. From here to here, well, that's A. So that means from one barrier to the other. So the length of that well It's basically the length of the crystal. Okay, so we're gonna keep building on this. Now let's pick an arbitrary set of quantum numbers. And we're gonna use a specific energy level or energy state for that set of quantum numbers. Therefore, if you relate those two, we can actually say that an energy state can be represented by a point in a quantum number space. So if you see, I have the three quantum numbers there, right? I have n1, in x, and y, and then z, right? I have my three quantum numbers, and I know that therefore I can represent those three quantum numbers by just one vector, right? So that's basically, I'm in quantum number space. So I can use this vector to represent my energy state, right? Because the quantum numbers are related to the energy state of a particle. So now let's actually plot a sphere with radius n. If you think of a sphere built with radius n, all the values of energy that lie on that surface of the sphere will have the same value. So basically, this is just a quarter of a sphere, what you see there, right? But anyways, it still helps to represent. If I get the energy here, or the energy here, or the energy here, or the energy there, or the energy there, all these values of energy are equal because they're all lying on the same surface of this sphere of radius n. And this radius, it's basically the representation of the quantum numbers that are representing an energy state. Therefore, all the values that are lying on the surface of that sphere have the same energy. Therefore, all the points within the sphere, now within, not on the surface, within the sphere, are quantum states that have an energy smaller than E of n. So basically, an energy smaller than the energy that is on the surface. And that makes sense, right? So within this sphere, I have values of energies smaller than the value on the surface that we've called it for now E of n, or E sub n. Now, I'm sure you guys barely learned, maybe even in high school, about quantum numbers when you were learning about the electronic configuration of different materials. And we all know that quantum numbers are only positive integers. We don't have quantum numbers that are negative. That's impossible. Therefore, and that's why you see, if you see there, the sphere is actually not complete. It's only a quarter of the sphere, because it's gonna be only in this plane where x, y, and z are all positive, because all the possible quantum numbers are always positive. Therefore, n values can only be defined in the positive octant of the n space. Okay? Now, I was talking about values of energy within the sphere and on the surface of the sphere. And I was talking about quantum states, right? A quantum state basically is a state of a quantized system that is described by a set of quantum numbers, right? So the number of quantum states with an energy that is equal or smaller than En. So equal or smaller than the energy that I have on the surface is basically proportional to the volume of the sphere. Now you want to tell me why is this important? This number of quantum states that have an energy equal to or smaller than the energy on this surface, because those basically are the states that can be quantized. And what does it mean quantized? That, well, that the electrons can be there, right? Therefore, if you get the volume of the sphere, you can remember, I'm sure, the volume of a sphere is 4/3 of pi times the radius cube and times pi. Sorry, 4/3 of pi times radius cube, right? What's the radius of here, of this? Well, it's n, right? We're using n as the radius of that sphere. And it's not a full sphere. It's only 1/8 of the sphere, right? Yeah, it's actually not. I was saying a quarter of the sphere. Actually, it's not a quarter. It's an eighth of the sphere. Sorry, I was saying a quarter. It's actually an eighth of the sphere. And therefore, this is giving me the number of energy states that have an energy equal to or smaller than En, equal to or smaller than the maximum energy. And now if I use the previous equation, because I have pi n cubed, now I have n, right? I can solve for n here, right? Because I have En here. So basically I can solve for n just taking this as a one single quantum number, right? Because anyways, n squared is equal to, you know, all know that, right? Nx squared plus ny squared plus nz squared. So I have this basically equals n squared. So I can solve for n and replace that here, sorry, and I'll get this equation, right? And so what is this? That's just the total number of energy states, right? That are quantities. So basically, we think about how are these energy states distributed. Now, if we take the derivative of this function with respect to energy, I'm actually gonna get the density of states. And what do we call the density of states? Well, it's basically, sorry, the number of energy states per unit energy in an interval d e. So in an interval, in a small interval of energy, how many energy states I have per unit energy. So just take the derivative, right, of the number of states with respect to the energy, and you get the density of states. And now you're gonna see something interesting here. A cubed, right? You see, it's basically a squared to the 3/2, right? So that's basically a cubed. And what is a cubed, guys? The volume, right? So that's why you see a V there. It's just because it's replacing a cube. So the lattice cube, we're assuming we have a cubic lattice, right? Remember, we were calling A is basically the length of the crystal, right? So we're assuming a cubic crystal. I mean, if you assume a cubic crystal, then you get this. If not, I mean, if it's not a cubic crystal, you can stop here, right? You can stop there, and that will be your density of states. If you have a cubic crystal, well, then you just replace, because you know that A cube is the volume, right? And you get that. So now let's actually see this graphically so you might understand this better, guys. You see there the density of states plotted versus, well, actually the energy plotted versus the density of states, right? You see this is a band. The M band, as I said, we're basically assuming this is the valence band. So in this valence band, how are my energy levels distributed? That's basically what the density of states, or this is basically the relationship between the energy and the density of states. So in this space, you see, in this little space, that's where you take the derivative. So the density of state is it's basically what's that small change of the number of energy levels in a small energy interval, right? So the change of this with respect to that. So if you see this function, this is a parabola, right? Because I have set of e and I have e to the half. So that's a parabola. So that's why you see a parabola. It makes sense, okay? And now you can see something interesting. At the lower end of the band, of the valence band now, or the M band, as you want to call it, what's happening? At the lower end compared to the upper end. Well, at the lower end, you see, the parabola is expanding as I go up in energy. So at the lower end of the band, I have considerably fewer energy levels per unit energy that are available to be occupied. So it's sort of, if you want to sort of understand this concept, you can think of a tall building, of let's say a huge building that those that you have in Guayaquil. And usually what happens is in the lower, or consider that huge building, in the lower levels, it has maybe 2 or 3 apartments, whereas in the upper levels, it actually has 10, 20, 30 apartments. So that's what's happening here. At the lower end of energy, or basically when I have a little energy, I have lower energy levels, or fewer energy levels, sorry, not lower, fewer energy levels per unit energy that are available. Okay? In the area within the whole curve is the number of states, that should be only of, sorry, the number of states that have an energy equal to or smaller than EM. So the area within this curve, the whole area, is all the states, or is the number of states that have an energy equal to or smaller than EM. Okay, that's for the free electrons case. What happens when we don't have the free electron case? So in actual crystals, in actual metals, for example. Wait, because we have the beryllium zones here, because we don't have a continuous, right? When we're talking about crystals, because remember, we have this sort of periodic arrangement, and we have the beryllium zones and all that. Well, the density of states now it's modified. And it's actually modified by the conditions that we have in the first beryllium zone. And that's why it's not a parabola like before, or well, it's sort of 2 parabolas, right? One concave up and one concave down. And they sort of meet at a point. So what can you understand from that graph? For low energies, because you see for low energies, the behavior is similar. So for low energy values, the electron behaves like a free electron. Therefore, it's the same parabola. However, for larger energies, I have fewer energy states that are available. So I don't have that case anymore as I had before, right? That the higher the energy, the more, or the higher the number of energy levels available. That's for the free energy case. So that's basically, let's say, for the valence band. Now, what happens when I have crystals, right? I have metals, actually. Well, remember, they don't behave fully as free electrons. And we have the brilliant zones, and they put certain conditions. So now, actually, yes, I have at low energies, I have a behavior like a free electron, but at high energies, I have fewer energy states that are available, and that's why it comes back, right? So it's like a parabola, but now concave down, or half of a parabola concave down. And therefore, the largest number of energy states that you will find in a crystal, in a metal, will be near the center of the band. You see, it's well, not exactly the center, but it's near the center, right? So it increases, and then it reaches a point where it basically fills, or the brilliant zones get all filled, and then comes back.
Sorry,
Yeah.
sorry, but I don't exactly understand what a state is. I don't know if is it the energy level or what is it exactly?
Okay, give me 1 second. I'll answer your question in a minute. Okay, give me 1 second. Let me just finish this. We just have 3 slides more. Okay, so I'm gonna steal 10 more minutes, guys. So I'm sorry. And then I'll come back to your question, Natalie. Okay, so we got the density of states. Now, what's the number of electrons per unit energy? So actually now, how many electrons I have? And I can actually use this concept of density of states. If I only multiply the number of possible energy levels by the probability for the occupation of these energy levels. What's the probability for the occupation of an energy level, guys? Or how do I determine that? With the Fermi function. The Fermi function gives me the probability for the occupation of an energy level. And if I multiply that by the number of possible energy levels that I can have within a band, so that means by set of A, I will get that number. However, remember Pauli principle, and you should have learned this already. Remember that Pauli principle tells me that each energy state can be occupied by 1 electron of positive spin and by 1 electron of negative spin. So I'm sure you guys saw that, right? Remember the spins of the electrons, right? So each energy state can be occupied by 1 electron of positive spin, and so this is a state, Natalia. And I'm not sure if that's clear, but an energy state is what you call S, for example. So remember, you have S2, let's say, right? And the electronic configuration, let's say 1s2, right? So you know in that state you have but 1 electron that has the positive and the negative spin, right? So that's an energy state. But anyways, I can come back to your question later. So that basically tells me that, okay, I have to multiply 2 because they can occupy two spins, or each energy state can be occupied by one electron of positive and one electron of negative spin. So that's the two. And then it's just times the possible number of possible energy levels and the possibility for the occupation of those energy levels, right? So I can multiply both functions. We already know the functions. Okay, so I'm just gonna get that, right? I can plot this, definitely. So by the way, so what does this mean now, right? It's the number of electrons per unit energy. So we can actually call it the electron population density, right? So basically, how many electrons I have within an energy level, right? And so I can multiply that, right? I can plot for that. I can plot this equation, and I'm gonna get something like this. This is just, I mean, you can plot it in your own computer, and you will get it. Now you see something interesting here. When t is approaching 0, and E is much lower than EF, or not much lower. E is just low. Is smaller than EF. When t is approaching 0 and E is less than EF, you can see something, right? N of E becomes what? 2 times Z of E. Oops. 2 times Z of E. Why? Because when this is happening, when I have E less than EF and T is approaching 0, this whole term becomes 1. So that's one case. It's just basically 2 times, and then it just becomes 2 times the density of states. Or now if I have a case when t is not equal to 0, so like this case, t is not equal to 0, and E is almost approaching EF, you can see what happens here. It's the same as we had before for the density of states, right? It's this sort of gradual change of the electron density. So now what's the area within the curve? The whole area within the curve is going to represent the number of electrons that have an energy that's equal to or smaller than the energy En. And we are always coming back to that concept, right? Now, let's actually calculate the Fermi energy, because I've been talking so much about the Fermi energy. Let's integrate. And let's consider a simple case to calculate. I mean, you can actually calculate this for other cases, and you actually will see that the result is the same. But let's do the calculation for t approaching 0 and E less than EF. So integrate that from 0 to the Fermi energy. You integrate N on N of E. Remember, this is the whole function, right? But remember, we're using t approaching 0 and E less than EF. So we're just integrating. If you remember, when this case is happening, when this case happens, this becomes just equal to 2 times Z of E, right? Remember? So I'm just integrating that. You can integrate it and you'll get this answer, right? Therefore, solve for E of F. So solve for Fermi energy. And ta-da, you got it. And you've defined this term. That's just another constant, right? It's just you call it M prime. M prime is just equal to the number of energy to the number of electrons divided by the volume of that unit cell, right? So it's basically the number of electrons per unit volume. That's just an easier concept, I guess. So even though, and this is actually the equation for the Fermi energy, and even though it might look quite simple, as I said, it actually doesn't limit the applicability of this equation. Because if you think about it, the number of electrons doesn't change with temperature. And you see there, this doesn't depend on temperature. The term that sort of depends on temperature is this term, right? But if you think about it, the number of electrons don't change with temperature. The number of electrons is never going to change. I mean, it's not that I increase temperature, I have more electrons. That doesn't happen. So because the number of electrons doesn't change, this equation has applicability. And it's actually quite a good value or quite a good equation that allows me to find the Fermi energy of different materials. And as I said, you can calculate this for other cases. You could integrate this for the other case, let's say when t is not equal to 0. So you can actually use the full equation or integrate the full equation. But you get a value that is similar to this one. And you can integrate even from 0 to infinity. And will give you the same result. Okay? So we've seen a lot of concepts now that I'm sure most of them, or if not all of them, are unfamiliar to you, and that's perfectly understandable. They will become a bit more clear once we start relating these concepts to the actual applications or to the actual properties of materials, and that will, I guess, might make things easier a bit, at least, because you will see, I guess, more directly the relationship between these concepts and the usefulness for the properties or for predicting properties of materials and for the behavior of different materials. But yeah, so be patient, because I know this is a whole bunch of unfamiliar concepts to you, but they will hopefully become more transparent when we apply them in the next modules. Okay, so now I have time to answer all questions. Okay, Natalia, so you had a question, so you can repeat them, and I guess everyone else that has any other question is welcome to ask. This is the end of the first module.
Yeah, I was asking about what state was exactly, but you already explained it, so I think it's clear now.
Okay,
Thanks.
Cool. Mari, you had a question. Mari's still there. Okay.
I had a question about the last class.
Okay, doesn't matter. Go ahead. You guys can ask questions about any, because this is the end of the first module, so you can ask any question about the first module. Any question.
Okay. I remember that you said electrons, the further from the nucleus, the looser they are. The less attractive for the nucleus they are. But it doesn't suppose the electrons where are closer the nucleus, they have lower energy levels.
Okay, I don't quite get your question. So when electrons are farther away, so like valence electrons, for example, that you all know that they are the electrons in the outermost region of an atom, they are loose, and that's why we consider, because obviously they're far away from the nucleus, so they're not attracted to the nucleus, and so they behave like free electrons. And I don't get the other part of the question. You can ask in Spanish if it's sort of difficult to put it in words in English. That's fine.
Es que yo pensaba que te referías a que cuando dijiste que los electrones están más cerca del núcleo, como que tienen, a ver, no, más lejos del núcleo tienen menos energía. Se supone que era al revés, ¿no?
No, a ver, yo lo que dije es que mientras estén más lejos del núcleo, no van a estar, obviamente no van a sentir esa atracción por el núcleo. Por ende van a estar más sueltos y por ende se comportan como electrones libres. En cuanto a energía, a valores de energía, pues ahí viene un problema enorme, porque y es algo que ni la mecánica cuántica considera. And that's actually the thing that, let's say this is the nucleus, right? And you have the first orbital, the second one, and let's just draw 3 orbitals, right? And this, quantum mechanics doesn't actually consider that the attraction of this electron, in, let's say, in the first orbital, is actually higher to the nucleus than the attraction that the energy of the second nucleus, the energy of the second electron, the attraction of the electron that is in the second orbital has to the nucleus. So what basically quantum mechanics does, let me just find some white space just to draw and explain this. So classical mechanics basically was considering, okay, the nucleus and a bunch of electrons all there, and that was it, right? At the same distance and nothing else. So nothing interesting, that's why classical mechanics don't work. Quantum mechanics, they do this, but they do this, and then let's say 1, 2, and then let's say the valence band, okay? So they do make a huge difference between the electrons that are in the valence band, so electrons that are, far away from the nucleus, and the electrons that are closer to the nucleus. They do make a difference, okay? So let's say that's the nucleus. They do make a difference, but they sort of englobe or make this just a one body thing. So they consider this a full one body. So they don't make actually the distinction, and that's a problem of quantum mechanics, but it still works quite well. They actually don't make the difference between electrons being actually the closest to the nucleus, or let's say in the first orbital, and an electron in the second orbital. They do not make that difference when basically they're considering all these equations, but they do make a difference between the electrons that are close to the nucleus and valence electrons, or electrons that are actually far away from the nucleus. They do make a difference between them. But and then about the energies, we can't really say, right, that that electron, it will depend on the energy levels, right? And we can say, okay, that electron is at that energy level, or is within that energy level, because remember that within a band, this is a band, right? We have energy levels within this band, right? We have energy levels within that band, and I will have electrons within that band, but I can't say that, okay, these electrons have higher energy, or that's, as I said, it's impossible to say the value of energy and the position that all electrons have. And that's why we use the Fermi Dirac and the Boltzmann distribution, because it's just more about probability. Any other question, guys?
I have a question. Well, I posed my question in the chat, but I can say it right now.
No, okay, let me, because I was reading the chat before. So Natalia said no electrons in that level. Okay, well, so the higher energy that the electrons have at t equals 0 occurs when f of v equals a half. No, okay. Well, not when t equals 0. Okay, so let's just go back to these two graphs here.
This is my question.
Yeah. Okay, so this is the question. Okay, so the Fermi energy is just a concept, right? It's just a concept that they said we need to define a level so that we know that below that level or below that energy, all energy levels will be occupied, and above that level, all energy levels will be unoccupied. And and Fermi came up with this, and he said, okay, let's actually do this, and that's why it's called the Fermi energy. So the higher energy that the electrons have at t equals 0, no, so when t equals 0, right, electrons can have different energies, and that's my point, and that's what I was saying to Mari. It's not that I can say, oh, so this electron has this energy and this electron has this energy. I don't know that, because there are billions, trillions of electrons in a solid. I don't know the exact energy of an electron, of one electron, I mean. But what I can say is that when t equals 0, if the electron has an energy that is equal or lower than the Fermi energy, then yes, though the energy levels that have that energy are occupied. And if it's higher than the Fermi energy, well, those electrons are that energy is unoccupied, or it's empty. Now let's go to the case when t is not equal to 0, and then yes, Jose. So let's say the definition of Fermi energy was so simple when t equals 0, right? Because it's simple. It says, okay, when it says when t equals 0, okay, if the energy is lower or equal than EF, then yes, you have a probability of 1, so that means all energy levels are occupied. If it's higher, then you have a probability of 0, therefore all energy levels are empty. But they said, okay, let's actually go to reality, because we know that it's almost impossible, and most materials in the world are not at temperature, at the absolute 0 temperature. So let's actually represent the case when t is not equal to 0. And they did that and say, oh, okay, wait, but now how are we going to define the Fermi energy? They were not, so they said, wow, what's the Fermi energy now? What's the problem? And they said, okay, actually, let's define it as the value of energy when the probability, so that means when the Fermi function equals 1/2. So that's the concept of Fermi energy. So now, going back to your question, when you say the higher energy that electrons can have at t equals 0 occurs when the Fermi function equals 1/2, no. The highest energy occurs at t equals 0. The highest energy can go infinitely. And electrons can have energies here. Electrons can have infinite energy. But for an energy level to be occupied, the maximum energy that electrons can have, yes, is the Fermi energy. And at that level, when t equals 0, I have a probability of 1 and a sudden change to 0, right? Because that actually happens when t equals 0. So I'm not sure if that makes things, I guess, the concept, because I see your question actually has a concept problem rather than, I think you actually had a problem in understanding the actual concept of what the Fermi energy is. So I'm not sure if this made things more clear, Jose.
Yes, I understood it now. I have a other question, but it's not about the the subject. It is about the lesson. The problems of the lesson will be mathematical problems or a mix
Um,
about
no.
theory.
So next week, well, I guess 2 weeks from now, because it's the lesson. It's not a quiz. A quiz is everything mathematic. Okay. And by the way, I'll post your assignment tonight or tomorrow. Okay. I'll post your assignment, guys. You have an assignment. Well, let me see. Actually, let me finish this. And let me see who's still connected. Okay. I'm gonna ask, given that's the majority of you, I have two options for you guys. I can either make the assignment available on Saturday, and then you have to submit it until Sunday next week, or I can make it available tonight or tomorrow, but then you have to submit it on Friday. Why am I asking this? Because I know you have 3 days of holiday next week, and I don't want to take away your time. If you want to rest or focus on other subjects, that's fine. But this is up to you. So if I post it today or tomorrow morning, you have to submit it on Friday next week. If I post it on Saturday, you have to submit it on Sunday next week. What do you guys prefer?
So in both cases, we're going to have almost a week.
A week. You will always have 1 week for every assignment. There will not be more than 1 week.
Okay.
It will always be 1 week for every assignment, and the assignments are sort of problem sets with some computer things. You will have to plot certain things in the computer, and I'll explain everything in the assignment tab.
So it is today or Sunday.
Or Saturday, and then you can submit it on Sunday next week if I post it. Yeah. It's up to you, but you guys have only 1 week to do any assignment, right? Regarding on when I post it, I can even post it next week. Let's say Wednesday, your last day of holiday. So Wednesday, I think 3rd of November. But then you'll have to submit it on November 10th. So it'll be a week. So regarding on when I post it, that doesn't matter. So it's more up to you. No answers?
From my
prefer that,
perspective, today, yes.
Yes. Sorry?
Today.
Okay, I'll post it tonight or tomorrow morning at the latest, okay? And then you have to submit it on Friday next week, okay?
Okay.
So the computer problems, so everything will have to be done by hand, okay? So you'll get a paper, maybe your notebook, whatever, an A4 sheet of paper, whatever, everything by hand. You take a picture or you scan it, and then you upload that. But there will be 1 or 2 problems that you'll have to do in a computer. For that, you're gonna print your code. Okay, you're gonna print it in a whatever paper you have. You're gonna print it, and you're also going to scan that. So I'm gonna ask you to plot something right in your computer. So you will plot it. You will obviously print that plot, but you will also have to print the code itself. So if you use Python, if you use MATLAB, whatever you use, you will have to print that code. And everything with comments, okay? So you comment on your code so I can understand what you're doing in your code. So if you write something in your code, you comment on it, right? And you say, okay, I don't know, I'm doing this for this or whatever, or define this range, whatever, right? But you comment on your code. So basically, what you're gonna upload to the platform is a set of pictures or a set of scans of your assignment. Because The problems you will have to do them by hand. They're obviously, most of them are mathematical problems, so you will have to write them by hand, resolve them by hand, and then whatever questions I ask you to plot on your computer, you plot them, you print that plot, but also you print your code, the code you use to plot that. Is that clear, guys?
So the
And what
assignment
kind
will
of
be
software do we have to use
like,
for that?
Any software you want. You can use Python, I guess, because all of you know Python, so you can use Python.
teacher. So
Yes.
we'll have a set of problems, and then in the assignment, I mean the Aula Virtual platform, we will be asked to upload the code
file.
and the graph,
No, you will be asked to upload a file.
a file of TXT.
No, a file. So the file will have photos or scans of your problems by hand, and also of your, or you can, if you want, you can also do a print screen, right? You can take a screen capture of your code and a screen capture of your plot, but that's part of a whole PDF. And in that PDF, you basically have different scans of base. I don't know if you use 2, 3, 4 sheets of paper to solve the problems. So basically, I want only one document where you have solved all the problems,
Plus the captures
plus
of
the code, plus the plot.
Okay.
Okay.
Can we use Jupyter?
You can use Mathematica. You can use any software you want. That's up to you. As long as I see the evidence, I just don't want to see your plot. I also want to see your code or the input. If you use Wolfram Alpha, for example, okay, use Wolfram Alpha. You're welcome to do it. But show me in Wolfram Alpha what you put.
Okay.
Okay, so you can use any software. That's up to you. As long as you show me the plot and you show me how you did that plot. Okay. Then you can use any software. And that's it. So that's the assignment. So you will have, I don't know, I'm calculating maybe 4 assignments in the whole course. Remember, the assignments don't count towards your theory mark. They count towards your practical mark. Remember, you can see the first slide, the intro, you have the marks distribution there. So quizzes and assignments, they go to the practical node, the practical grade. Lessons and the exams go to the theory mark. So 2 weeks from now, you have a lesson. You don't have a quiz. Therefore, not everything is going to be mathematical. Quizzes are mathematical. Quizzes are problems. Quizzes are, you write by hand and everything. Lessons, they do have a theory component, right? So they're different. They're more like exams, but it will be a short lesson. It'll be like a 10-minute lesson or so, quite short. Yes, Mari.
David, please, could you give us an example of what we will plot? Maybe, I don't know, energy band diagram or what?
Let's say the Fermi function. The Fermi function, you will plot it for different temperatures, for example.
Oh, okay.
But it's something like that. So you will plot the Fermi function because you can just go and Google the Boltzmann constant. You can just go and Google the mass of the electron. So you input all those values, and then you just define a set of temperatures and you plot it for a set of temperatures. It's not going to be that, but it will be something like that. So it will be plot the Fermi function for a region temperature, and then you will have to interpret the plot, and I'll ask you to do that. But that's part of the question. But I mean, it's nothing impossible. It's nothing that, oh, I can't do this. No. It's just a matter of literally plugging in the values and plotting. It's not something that you will have to think, oh my gosh, what am I going to code and what am I going to plot? Definitely not. Is that clear?
Yeah, I think it's clear. No.
Okay. Well, you'll see your assignment, definitely. You'll see your assignment, and then you can ask me any questions, obviously. Yes, Miguel.
Would you please help us with the the dates of the quizzes and the lessons.
Okay, so as I don't have the date of the day of the quiz yet, but it might be a quiz. You guys might have a quiz actually on November the 10th. So November 10th, you might have a quiz, but you will definitely have a lesson November. Oh, actually, no, wait. That's actually no, because November 3rd. No, sorry. November 10th is your lesson. Okay, November 10th is your lesson.
Okay.
And November 17th, you might have your quiz. There might be a quiz. I'll confirm that. But definitely November 10th is your lesson. As I said, it's a 10-minute lesson. Nothing. If you remember the lessons like ceramics engineering or materials engineering last semester, the lessons were quite short, right? The exam was large, but the lessons were 10 minutes or so. So it will be like that, 10, 12 minutes.
Okay, but teacher, I think that do you think that that amount of time will be enough? I mean, we are going to solve kind of we'll have
for the lesson, yes.
Equations
for the quiz,
and
no. For the lesson, yes, because the lesson is not mathematical. There will not be like a mathematical problems of integrate or derive this. No, that will be for the quizzes, and that will be for the assignments. In the assignments, you will have to do derivations, integrations, and you will have that in your quizzes. But for lessons, yes, because lessons are more theory or a small numerical problem, but it's short. Right?
It's not about. There won't be cases like in ceramics or metals, no.
I mean, I'm never gonna teach you something that I didn't. I'm sorry. I'm never gonna test you something I didn't teach you. I can't tell you what the lesson is gonna be like, but I can tell you that there will not be something that I haven't taught you. So you'll have to think. Obviously, you have to think. In my lessons, my quizzes, my exams, you have to think. It's not something right away, like from the slides you copy and paste it. No, you'll have to think. But I mean, anyways, your brain is already thinking because quantum mechanics is already by itself is difficult. It's quite a complex subject, and so I'm don't worry. I mean, I'm not gonna be testing you on. I don't want you to become Einsteins. I don't want you to derive expressions a lot, and I don't want you to understand the most fundamental concepts of everything, because you're not physicists, so I don't want you that. But definitely I want you to understand these key concepts and what I've explained, what I focus on, those are key important concepts because they're gonna help us to define how materials behave in different properties. So yeah, I mean, there might be a case, but it's gonna be something that you can just relate to something we've seen. It's not gonna be something impossible. You will have to think, yes, you'll have to think, but I mean, that's the point of a lesson, right?
Yes, I get it.
Okay, that's it, guys. I guess I took away more than 30 minutes. Okay, but thank you, guys. Any questions? I'll upload the assignment. If you have questions regarding the assignment, you can text me. I don't understand this, and I'll definitely help. Okay.
Thanks, David. Have a good day.
Thank you, guys. Have a good night. Actually, good night. Hope the strike is not going strong there. Here, we're actually with big problems here, but hopefully this is going to stop. Bye, guys. Take care.
Thanks.